Thank you very much. And now for something completely different. I've been wondering a couple of hours if my name would fit here. It does. It's a good start. I'm a biostatistician. When I first received the invite to speak to you, embarrassingly, I thought it was a spam email. Not because of low self-esteem, well, not only that, but because I haven't touched neurology relevant data in well over a decade when I finished my PhD. But before you start running away, I will be talking on methods that are relevant to any field, and I think they're very relevant to neurology as well. So this is the outline of my talk. I will give you a little bit of background as to what is meta-analysis, what are the potential issues, the biggest problems we encounter, what, in my view, are common mistakes. These might be personal opinions, others are more well-validated, and a summary. So, what is meta-analysis? And when in Rome, I should say that meta is a Greek word meaning after. So meta-analysis is post-analysis, more or less. And it's synthesizing existing evidence to answer clinical questions. It's a relatively young and dynamic field of research, so the term was coined around in the mid-70s. And there has been ongoing methodological development for a number of years. The methodological activity running in the background does reflect the importance of meta-analysis and its potential to provide conclusive evidence. And there are a few different techniques under the same umbrella term of meta-analysis. So besides the standard meta-analysis of aggregate data, we have meta-regression, individual patient data meta-analysis, and network meta-analysis. And I'll try to touch them all in this short talk, which is a bit of a challenge. So excuse me if I'm very brief on areas that you're aware of. So this is a slightly different evidence pyramid to which, compared to what Professor Bernstein presented before. So here we have systematic reviews at the top. This is where the previous pyramid evidence stopped. So in most areas of research, systematic reviews sit right at the top. Systematic reviews of randomized controlled trials is seen as golden evidence, basically. I'll start with an aggregate meta-analysis. So when original data are unavailable, so when we don't have the data from the clinical trial, as unfortunately is the case these days in most of the investigations, we try to combine existing evidence in a two-stage process. So we retrieve the relevant summary statistics from various papers, and using meta-analysis techniques, we're trying to estimate these all-important mu. And this is the only formula I will give you today, you'll be glad to know, which is the overall effect estimate, the overall effect of a particular intervention, say, in a particular population. And this is what a meta-analysis forest plot looks like. The squares represent the weight of the particular study in the meta-analysis. The lines, the confidence interval, what's the variability of the effectiveness. And this is the overall effect, basically, this symbol. So what is meta-regression? Usually it's on top of an aggregate meta-analysis, and it tries to explain the variability in the effect, and does associate patient and particularly study characteristics, moderators that is, with study effect estimates. So here is an example associating the median age within a study to the mortality rate, for example, and we see obviously the higher the median age, the higher the mortality. And what is these days seen as the golden evidence in meta-analysis is individual patient data meta-analysis, which requires patient data from its study. And it's able to deal with many of the problems that are embedded in standard aggregate meta-analysis. There are much improved moderator analysis compared to what we have with meta-regression, and there are two different approaches, one stage and two stage. For example, in this individual patient data meta-analysis, we have the main effect here, and we have the moderator effect there. There's also network meta-analysis, which is even younger and more dynamic, which allows indirect comparison of exposures. For example, if I have an RCT comparing drug A to drug B, another RCT comparing drug B to drug C, but there's no direct comparison between A and C, network meta-analysis can allow that comparison. The problem is, one of the problems is that it's not relevant to all fields, and it also can be aggregate meta-analysis, which has the same problems, or even more problems, as standard aggregate meta-analysis, or we can have individual patient data network meta-analysis as well, which is seen as more powerful. So what are the problems? All this sounds very nice so far. So one of the biggest problems is heterogeneity. So when the effect of the intervention varies from one study to the other. And there are many reasons why that might be the case. It might be clinical, so we might have different populations, slightly different interventions, different outcomes, or even follow-up times. And also there might be differences in the design of the trial, in which case we have methodological heterogeneity. But this is one of the biggest problems in meta-analysis, because detecting, quantifying, and dealing with heterogeneity is very difficult. And this measure, the I-squared, has become the mainstream measure to quantify heterogeneity. So when we do standard aggregate meta-analysis, there are two schools of thought, random or fixed. So why are they different, and what are the underlying assumptions? So in a fixed effect meta-analysis, we're asking what is the average result of trials conducted to date. But obviously, from my point of view, and I'm very much a proponent of random effects meta-analysis, the question which we want to be asking is what is the true treatment effect to all populations? And there are various assumptions, unfortunately, with the random effects approach. So we assume that there are normally distributed trial effects, that the varying treatment effects across populations, and an advantage is that it's more conservative because we get wider confidence intervals, for example. But another complication is, like I said before, detecting heterogeneity, which actually drives if we can perform a random effects meta-analysis or we should proceed with a fixed effects one, is very difficult. And when researchers fail to find such heterogeneity, they are reassured and they proceed with a fixed effect meta-analysis. And there's a fundamental difference in the weighting in the methods, in the meta-analysis methods with its process. So fixed effects, a fixed effect method just weights by the size of the population. Larger trials will have a larger weight in the meta-analysis process. While, for example, within the random effects framework, it's the inverse variance weighting. It's a different approach that potentially does not do that. So how do we detect heterogeneity? Even if we want, like I said, to proceed with the random effects model, we need to identify heterogeneity first. And there are various ways to do that. The problem is they all share the same limitations. So especially for small meta-analysis, it is quite common for these methods to fail to detect heterogeneity. So my position is that overall meta-analysis research estimates are less conservative than what they should be, just because we have failed to identify the heterogeneity and take it into account, which will lead to more false positives. Another potential problem is publication bias, which is a well-known phenomenon and possibly the greatest threat to medical research. So smaller studies that demonstrate positive effects are cherry-picked by us, by publishers, by the media, and they are pushed very quickly into the open. While other equivalent small studies that didn't find these positive effects, we didn't pursue to publish, the editors weren't interested, and so the media wasn't either. So what's the consequence of this? Studies that demonstrate a positive effect, for example, a treatment that works, are more likely to be small. And when larger studies try to replicate the results, they often cannot. And meta-analysis, as a consequence of that, will overestimate effect sizes unless publication bias is taken into account, which is very difficult. So how big is this problem? So we had a paper a while out. I won't go into the details as to what this means, but keep in mind that this value, this relative risk, needs to be close to 1. If it's above 1, it means that results that show a positive effect are more likely to be published. Ideally, in all the meta-analysis, we would expect that to be 1, because that's what we see in later years. So what this graph tells us, that there was large bias in the early years, and over time it has been improving over time until current time, mainly driven by new criteria pushed forward by publishers and us taking them on board to trying to improve the quality of reporting, which has reduced publication bias. Another problem is, so this is based on all the data from the Cochrane Library of Systematic Reviews back in 2013. But on a study-by-study basis, on a meta-analysis by meta-analysis basis, there's a big problem in identifying small study bias, because the tests that exist generally need 10 or more studies, and only around 11% of all meta-analyses have 10 or more studies. So for the remaining 89%, we simply do not have enough power to identify this problem. And ironically, in this case, the fixed effects approach is slightly better. There are methods that are being developed, but they all rely on making particular assumptions. So this is a recent example of potential publication bias. It was a paper in the BMJ. It's not in neurology, I'm afraid, but it's very topical. It's about vitamins D. So here you can see the meta-analysis that shows a positive effect for vitamin D. And on the basis of that, for example, the NHS, the National Health Service in the UK, would consider giving everybody of a particular age vitamin D supplements. But if we look more closely, and if we organize the graph by the size of the study, you can see how the smaller studies have much larger effects, and these become smaller and smaller as the size of the meta-analysis increase. So basically, we see no effect whatsoever for the largest three studies, and the biggest effects are driven by small studies. This is a typical example of potential publication bias, basically, how the overall effect is driven by the small studies. And why is that important as well? Well, size is another consideration in meta-analysis as a potential problem. When we do all this work, and if you have done a meta-analysis, it's a lot of work involved, and you run the risk of finding no papers that are relevant after you apply your inclusion and exclusion criteria. Or you may be left with 2 or 3 papers. Now, we found that 34% of all meta-analysis in the Cochrane Library were only based on 2 studies, and around 53% included 2 or 3 studies. So over half the meta-analysis conducted only rely on 2 or 3 studies. And this small size of meta-analysis compounds the heterogeneity and publication bias issues, just because we cannot test enough to see if these problems exist and to take them into account in our analysis. Another potential problem is poor study reporting. And again, if any of you have done meta-analysis in the past, you will relate to this. So papers, especially older papers, do not report statistical measures required. For example, the standard deviation, the measure of the variance for the effect, is the one that's usually missing. Or report statistics that need to be transformed into something common across all studies. And it's generally good practice to contact authors for clarifications, but people move jobs, especially for older studies. Unfortunately, people may have passed, so it's very difficult to do that consistently. And there are certain methods that try to account for this, but again, they come with certain assumptions. So again, it's not very easy to do that very convincingly. Now, the reporting standards, like the consort and strobe statements, have helped a lot and have greatly improved the situation in reporting. So meta-analysts have benefited from that profoundly. Now, all these considerations that are touched are mainly about standard aggregate meta-analysis. So how do these relate to meta-regression, for example? Well, like I said, meta-regression attempts to explain heterogeneity if detected. And the small study bias is relevant, but there we can use the small study bias, as a predictor of the study effect size. So we can see if that's what drives the effect we have observed in the meta-analysis. It's problematic to aggregate at the study level patient characteristics. So age, sex, for example, this is not a recommended way to analyze them through a meta-regression because of ecological fallacy, basically inferring for an individual from what we observe for a group. And the biggest problem with these types of analysis is that they're underpowered to detect anything but massive associations. So it's an analysis of 10 points, basically, if we have 10 studies. And the problem is compounded if we have categorical predictors, binary predictors, etc. Now, for individual patient data meta-analysis, these are very time-consuming and very complex undertakings. But we can control for available study and patient characteristics very well. Heterogeneity is less of an issue because we can control for these. And moderator analyses are much more advanced. Now, another problem that we don't usually see with meta-analysis of aggregate data is missing data, basically, just because we analyze at the patient level. So we need to use advanced techniques like multiple imputation to overcome that. There's a debate that I won't go into details about two different ways to analyze the data, one stage versus two stage, which again needs to be a consideration in any protocol. And the small study bias is still relevant, but less so, because it's partly addressed through the weighting. But what also we see here, that's not necessarily a problem in aggregate meta-analysis, is the high response rate, which is critical. If I'm following a field that just published an aggregate meta-analysis on 90 trials, for example, unlikely as this is, I cannot follow it up with an individual patient data meta-analysis to find particular moderators that make under which the intervention works and end up with 15 of these 90 papers. Nobody's going to trust my findings. So a high response rate from the potential pool when you do an individual patient data meta-analysis is very important. There's the network meta-analysis, again, similar considerations. So heterogeneity and small study bias are still very relevant, and we have additional assumptions. The one that's new is the consistency. Basically, when we infer what the indirect comparison between A and C is, it needs to be consistent with what we actually observe if there is a study or a group of studies that have reported on A between C. It's a bit complicated, so I won't go into details, but come and speak to me if you're interested in this particular type of meta-analysis. So from my point of view, what are the debatable points and common mistakes? And what can we do to improve meta-analysis? So, like I said, I do a lot of work. I end up with two studies. And this is largely driven by my role as a reviewer in statistical and clinical journals. So I end up with two studies. What do? Some people say you shouldn't meta-analyze two studies. I disagree with that just because there is information there. Despite all the problems that I told you, there is almost impossible to quantify heterogeneity with two studies. We cannot test for publication bias, etc., etc. There is information in the two studies that we need to try to harness. We will be discarding it if we don't, which I think is a waste. I run the heterogeneity tests, I calculate I-squared, and I don't find anything. Is this good news? Not necessarily, because especially for small meta-analyses, and like I said, over 50% of meta-analyses have 2 or 3 studies, methods to detect heterogeneity are very likely to fail there. So if you try to calculate its confidence interval, which is not very challenging, you'll see something extremely wide, which reflects how uncertain we are about these estimates. So we need to consider some sort of sensitivity analysis there. Another thing I come across in reviews is arbitrary thresholds for heterogeneity. So I found small heterogeneity, 20, say I-square should have said ranges between 0 and 100 is a ratio. 100% is impossible to get. 99.9 says massive amounts of heterogeneity. 20% is small. What I see when I review is people who have found 20 or 30% heterogeneity and decide to discard it because it's not that high. I disagree with that because random effects models that will take into account even that modest amount of heterogeneity are better performing. So we are doing a better analysis by using it in the model. Another measure that quantifies heterogeneity is Cochrane's cube, which is a test that tries to do so. It's underpowered, and I-squared is using it to calculate heterogeneity anyway, so it's either superfluous or underpowered, so I'd say do not use it at all. What if I find no evidence of small study bias from 7 studies, say? Again, that's no surprise. Like I said, we need at least 10 or more to be able to meaningfully infer something. Even then, it will be difficult. So I would say consider a subgroup of newer, large, or high-quality studies in that case to see if the results change. And consider other sensitivity analysis or even dedicated methods, or like the trim and fill method. What if I have a meta-regression of 20 studies? That will be underpowered to detect almost anything, so it's largely meaningless. Still do, but discuss it as a major limitation, that you're underpowered to identify almost anything. Anything except massive effects, basically. I'm trying to do an individual patient data meta-analysis, and I end up with a modest response rate. Well, I would start by saying use one-stage IPD and compare the characteristics and the quality of responder and non-responder studies. If across the two groups, the responders and the non-responders, we have very similar characteristics, I would trust your IPD more than if that wasn't the case. So, what to take home? Mainstream approaches are a bit contradictory, random effects and fixed effects, when dealing with both small study bias and heterogeneity. So heterogeneity is dealt by random effects models, but the weighting is problematic when we have small study bias, in which case fixed effect is better. So currently, meta-analysis of 2 or 50 studies sit at the top of the pyramid, of the evidence pyramid I give you in the second slide. For me, that's wrong. Because if it can be even worse. If a 50-study meta-analysis has identified considerable heterogeneity, and chances are it will be highly heterogeneous, it's seen as a weakness, while a 2-study meta-analysis for which we fail to identify existing heterogeneity will be seen as even better potentially. So I think when we read meta-analysis, we need to be very aware of the number of studies meta-analyzed. Be conscious of the limitations of heterogeneity and estimators of I-squared, and report the uncertainty in all cases. And what are the solutions to all this? Well, we need newer methods, and in my view, we need sensitivity analysis to demonstrate that our findings stand even if we assume high heterogeneity, which it's very difficult to pick up, or publication bias, which again is difficult to pick up on a meta-analysis by meta-analysis basis. And the tone in the discussion of the paper should reflect the realistic strength of evidence. If you have two meta-analyses, I would take that into account in the discussion compared to when you have 20, say. That's it. Thank you.
Thank you very much, Dr. Kontopantelis. You have been taught about many different approaches to the meta-analysis, and now we have time for a few questions. Please, Professor Korchin.
Thank you very much for the excellent overview. Thank you. I have 3 points I want to talk about. One is that when you do these studies, like the forest plots, and so in any study, in any scientific study, you must have a hypothesis at first. But in looking at the first plot, you usually do not. You say whether it's on the right side or on the left side. And this is inappropriate, and of course it limits the statistical significance of any results that occurs there. So maybe you can answer this. The second is the issue of the outliers.
Can I start before my memory is not like it used to be? So
you're talking.
you're quite right, but it's strictly down to the inclusion and exclusion criteria of your meta-analysis. The assumption is that the hypothesis is within the randomized controlled trials or observational studies you have included in your meta-analysis. For example, that vitamin D improves quality of life or improves other outcomes. So you're quite right that it's not as specific as in randomized controlled trials, and it should be more explicit in this meta-analysis, but it does share that hypothesis of the randomized controlled trials you meta-analyze.
So you assume that in Cochrane studies, they always look at the assumptions and they exclude studies which do not follow the same assumption?
So that's a problem. That's heterogeneity, basically, of the intervention, because we assume that the intervention is the same across all the trials, and the hypothesis is the same. So that's partly where this heterogeneity comes from, which is, like I said, a big problem.
Thank you. So the second issue is about the heterogeneity and the outliers. And I think the outliers are extremely important, and you should really pay attention to. So if in a meta-analysis you find an outlier, maybe it's because the base population was different. Maybe in some area of, in an study in India, they had a different genetic or environmental factors, and this is a reason to look at this more specifically, and this is a basis for better data collection. And the third point is about the limitation of the meta-analysis that you have mentioned. So of course, if to take it to extreme, you meta-analyze data which are not similar to the base population. So you take the median effect, but the median effect can be, the population can have different baseline studies, so one is skewed to the right and the other is skewed to the left, and combining them is maybe or not show important differences, may negate important differences. So I think the solution to this, in addition to the important points that you've made already, is to have the raw data. And the raw data should be made available. And in fact, there are studies, there is a tendency in the world to have the raw data. The best example is ADNI, the Alzheimer's Disease Neuro Initiative, where you can get all the data, you can go to the website and find the data there, analyze it yourself. So the The raw data are there, and I think even the industry is now recipient to this idea, and they provide data, not all of them, not to some extent, but at least, let's say, for placebo-controlled studies, the data on the placebos are so important, and the data should not be, should be there, so that we can see what is happening, and I think this is an important point forward.
I think you have made excellent points. I didn't touch on outliers, and you're quite right. That's part of the sensitivity analysis, excluding those or looking into what caused the heterogeneity in those. And you're absolutely right about the trials, and well done to you. You are the exception, though, because trials cost money, and as you know, PIs want to hold on the data for as long as possible because their careers are built on that. I know that there are a lot of initiatives, they're through Cochrane or through pharmaceutical companies that have tried to address that, and we are now in a better place compared to where we were 5 years ago, but it's still a long way to go, an uphill battle. And that will allow individual patient data meta-analysis, which don't have that many limitations, and allow us to do much more refined analysis, as you said. So yes, hopefully that will be the future. But the current models of individual patient data meta-analysis are still embryonic. So you contact everybody that you know has published something, you offer them co-authorship. Hopefully they haven't fudged the data and they're open to sharing. And then it's a long process to get the data, get them in the same format, and we need infrastructure to standardize this as well. So the pharmaceuticals have made a step forward, and hopefully we'll get there sooner rather than later. But yeah,
Thank you.
Thank you very much.